Bismillahirrahmanirrahim. Assalamualaikum and good day. We are now on chapter 9 entitled as linear momentum and collisions. So whatever we've learned from chapter 1 up to chapter 8 previously consists of many approach to solve problem in physics. However, some of situation given to us have not with complete information so that we can solve it by using forces approach or kinematics approach or energy approach to solve the unknown asked in the questions, right? So now in chapter 9 I'm going to introduce another concept or method that we can simply solve problems, okay, with a very minimum information given. So where we are going to learn about linear momentum. If we refer to this diagram given here, you have two masses, okay. These two masses having each of them having different velocity, okay. This m1 having v1 into this direction and this m2 having v2 into this direction. However, these two objects are interacting with each other by the F, okay. F21 means that F applied on object 1 due to object 2. So remember in the middle here you put the word on. Okay, so F2 on 1. So means 1 is the one that experiencing the force. The dual is M2. Alright. And for M2 is experiencing F12 means that F, okay, from object 1 on object 2. Right. This is similar to action-reaction or Newton's third law. So in terms of F12 is equivalent to negative F21. They are same in magnitude but in opposite direction. If we consider now the whole things here as a system, okay, then we can have this kind of addition. In previous approach, okay, I told you before that you are not going to add up between F12 and F21 because we only consider one object at one time as a system. Now we are combining these two masses, take it as a system. So the force F12 is add up with F21 must equivalent to 0 because they are same magnitude but in opposite direction. So if we want to open up F net based on Newton's second law, okay, F net is equivalent to MA. Alright, so now this is the force experienced by object 1, okay, by M1. And this one is the force experienced by the object 2. If we add them up, okay, remember it must equivalent to 0 because we consider the whole system, the whole things or the two objects now as a system. And let's open up more for A. Okay, A1 is dv1 over dt and A2 is dv2 over dt. Okay, since m is a constant, you may rearrange the m, okay, times with a v1. So you have this method or pattern. Then we know that, okay, we can simplify this equation into this, which is d m1 v1 plus m2 v2 over dt equivalent to 0. So definition of linear momentum symbolized as P, okay, of a particle or an object that can be modeled as a particle of mass m moving with a velocity v is defined to be the product of the mass and the velocity of the particle, whereby P is equivalent to mv. Right. Since the m is a constant, right, so means that P direction is according to the V direction because P and V are the vectors. Okay, So bear in mind that P here is a vector, therefore it has components, okay? It has X component, Y component, and Z component. Newton's define linear momentum or name it as moving characteristic of a particle. So momentum is actually a Unani word, okay? Means that motions, okay? So means that this is a character, okay, where we evaluate one object having some velocity. So this is a kind of character of the object, which is known as momentum. And why is it the name of it is linear? Because we are considering only linear movement, okay, as of now. So based on Newton's second law, okay, F equivalent to ma, F net equivalent to ma. So our A just now is dv over dt. So we may rearrange the m, bring it next to the v. Then you are going to have is also equivalent to dp over dt. What does that mean? The time rate of change of linear momentum, d means change, right? Is equivalent to delta. Okay, the time rate change of linear momentum of a particle is equal to the net force acting on the particle. So in simple, we also may put it like this. Okay, in simple. So let's do the analysis model for isolated system, okay, where we are going to consider about momentum of it. So similar to the diagram that we used from the beginning, okay, we have d m1 m2 m1 v1 plus m2 v2 over dt, or the rate of change of momentum, is equivalent to 0. Okay, so this item is actually p1 and this item is actually p2. Alright, so we know that P total must equivalent to a constant. Change in P total must equivalent to 0. Alright, so from here, okay, we have, in other words, P initial must equivalent to P final. With regard of this system, okay, our P initial consists of 2 because we have 2 masses, right? So momentum for particle 1 or mass 1, okay, initial, plus momentum for particle 2 initial must equivalent to momentum for particle 1 final plus momentum for particle 2 final. Right, since we know that momentum is a vector, it has component, so we have to consider for the rest of the component. This is for X component, this is for Y component, this is for Z component. Right. Whenever two or more particles in an isolated system interact, the total momentum of the system does not change. Okay, for energy, we call the system is isolated whenever there is no transfer of energy. It is isolated when no transfer of energy across the boundary. This is for energy, right? For momentum, okay, no external forces on the system. Then we are valid to use. We are allowed to use this one. Why is it so? Because just now, okay, sum of F is equivalent to change in momentum over time. So if you want to have, okay, delta P is 0, the sum of the F must equivalent to 0. What does that mean by the sum of the delta P 0? Delta P 0 means P final minus P initial is equivalent to 0. It means that P final equivalent to P initial. Back to this one. Right? For 9.1, okay, the archer. a 60-kilogram archer stands at rest on a frictionless ice and fires a 0.03 kilogram arrow horizontally at 85 meter per second. With what velocity does the archer move across the ice after firing the arrow? Okay, it's like explosion case. Okay, the archer going to experience a recoil velocity backward. Okay, in opposite to the motion of the or direction of the arrow. Okay, so this is the information that we have. Okay, v of the our arrow, okay, is 85. Initially is at rest, okay, in terms of x direction. Okay, so based on conservation of momentum, delta p total must equivalent to 0. Okay, where we have p final equivalent to p initial. Okay, what we have here, okay, initially the archer and the arrow, both of them are at rest. So finally, okay, the archer has movement, and also the arrow also have movement, right? So based on this, okay, rearrange the equation. Our interest is about the archer, the speed of the archer, the velocity of the archer. Okay, so you will have this pattern of equation. Substitute, then you will have the v, okay, final for the archer, which is negative 4.25. What does that mean by negative? Okay, it means that it is to the left. Now, what if the arrow were fired in a direction that makes angle theta with horizontal, right? How will that change the recoil velocity of the archer? Okay, now, so the arrow, instead of moving completely horizontal, okay, it has theta, okay, with respect of the horizontal. So this is our V2 or V final of the arrow, okay, V2 final having theta with the horizontal. So means that our V2 has component. We have V2 V2F, V2 final in term of X, which is V2 final cos theta, and V2 final in term of Y, which is V2 final sin theta. Alright, so make use of conservation of momentum. P final is equivalent to P initial. Okay, P initial of object 1, the archer, P initial of the object 2, which is the arrow, both of it at rest. So it has no V, therefore it has no momentum. Okay, it just like the case of explosion, remember? So V of the archer, P. So P of the archer final plus P of the arrow final must equivalent to 0. But okay, for our arrow, okay, its V2 final is in term of V2 final cos theta, because it makes an angle just now, right? So it has in term of this, right? So rearrange this equation, make our V1 final as the interest, because this is the velocity final of our archer, right? So we are going to have this equation, right? Means that, okay, for sure V final of the archer will be less in comparison to the previous part, which is this one, isn't it? Because we have cos theta here. It depends on the theta. Okay. So next is analysis model, non-isolated system. Okay, still on momentum, right? So let's recall sum of F is equivalent to dP over dt, change in momentum to the respect of time. If we rearrange this equation, dP is equivalent to sum of F times dt. What does that mean by dP? Is also equivalent to change in momentum. Okay, change in momentum means that momentum final minus momentum initial. Alright, so what was this? Okay, this is if we consider only magnitude. This is a modulus representing only magnitude considered here. This is must be equivalent to integration of sum of f to the respect of dt. Okay, this one, change in momentum here, also known as impulse. Okay, symbolized as capital I. So, change in momentum, also known as impulse. Okay, what is impulse? Impulse is actually a measure of change in momentum, how big the change was. Okay, so it must be equivalent to integration of summation of f to the respect of t from t initial up to t final to have this process done. Right, so if we refer to this, right, the sum of f in term of average, okay, must equivalent to integration of sum of f to the respect of t, okay, times 1 over delta t. So impulse is defined as the f average times with the delta t. So rearrange this, right? So bring this one up here. Okay, so impulse is f average, sum of f average times delta t. Okay, or bear in mind, this is equivalent to change in momentum. Right, so in simple, f average is actually considered as a constant force. Okay, a real case is actually like this. If you plot f versus t for the case of a momentum change or collision or explosion, you have this kind of method or graph of f versus t. So over the time, there is starting from t initial is 0, then it's increased, okay, reaching its maximum value, and finally becomes 0 again. So this is the real, okay, force, okay, involved. If we calculate area under the graph, okay, it's f times t, right? So f times t by definition is known as impulse. So area under the graph here is the impulse. Alright. But since this is approximately equivalent to f average, okay, what does that mean by f average? Okay, if we refer to this graph, okay, from f that we have maximum value here, we have minimum value here. Okay, we figure out f average. Okay, approximately is equals to f average times with a t. So area here now is known as average impulse also. Okay, in simple. Right, so this is by considering the f is a constant force. Okay, for this case, it's now considered constant net force. In the real case, it's actually not a constant. It starts from 0, reaching maximum value, and finally becomes 0. But this one is approximately agrees to this one. Okay, and you may refer to this. The unit of impulse is Newton dot second, or equivalent to the unit of change in momentum or momentum simply. For the case of collisions, okay, we have to apply impulse approximation. We are going to assume one of the forces exerted on particle X for a short time, but is much greater than any other force present. So in this case, okay, we are going to represent the force that effective in this case of collision is F average. Okay, approximately agrees to the concept. So change in momentum again equivalent to impulse, equivalent to F average or F net times delta T. So this is a force that causing the damage. Right. So example 9.3, how good are the bumpers? In a particular crash test, a car of mass 1,500 kg collides with a wall as shown in the figure. Okay, the initial and final velocities of the car are V1 initial is equivalent to negative 15 I meter per second. V final is equivalent to 2.6 I meter per second, respectively. If the collision lasts 0.15 second, find the impulse on the car during the collision and the average net force exerted on the car. Okay, so this is the situation before and this is the situation after. What does that mean by negative? It's to the left, it's to the right. Okay, this is a real physical diagram of it. Okay, so impulse is equivalent to change in momentum, is equivalent to momentum final minus momentum initial. There is no delta here, okay. Okay, mv final minus mv initial. So it's equivalent to m delta v, in other words, right? So substitute, whenever you substitute the v, remember this is a vector, this is a vector, because impulse also a kind of vector, momentum also a kind of vector. So the negative sign here you have to bring along. Okay, it has meaning. So our impulse could be positive, could be negative, okay, showing the direction. So we have positive 2.64 times 10 to the power of 4 I kilogram dot m over s, or this is equivalent to Newton dot second. Okay, so to calculate the average involved in the case, okay, is equivalent to I over delta t. Okay, so this is coming from impulse is defined as sum of F average times with the delta t. So rearrange the equation because our interest is to figure out the F average. You will get 1.76 times 10 to the power of 5 I Newton. What if the car did not rebound from the wall? Suppose the final velocity of the car is 0 and the time interval of the collisions remains at 0.15 seconds. Would that represent a larger or smaller net force on the car? So again, it did not rebound. So means that impulse is equivalent to delta P. Again, there is no symbol of delta here. P final minus P initial. So if it does not rebound, it means it's remain at rest or stick to the wall or stop finally. So P final will be 0 because P final consists of M V final, which is it stopped. So V final is 0 and P initial is M V initial, right? Yes, we do have V initial, which is negative 15 I meter per second. So we will get our impulse right now. Okay, 2.25 times 10 to the power of 4 I kilogram dot meter per second. To calculate the F average, we are going to have I over delta T. Again, this is your answer, which is give us smaller net force. Smaller net force, okay, whenever it does not rebound. Alright, so now collision in one dimension. So if we refer to this diagram, we have two kind of collisions. Okay, it's due to the direct contact, okay, between two objects. Okay, so by means of forces involved here. Due to the forces involved here, okay, there is effect in this collision. And in second diagram here, this collision, okay, by means of the force as well, but then, okay, is not in direct contact because it's due to the charge, okay, repel in charge because they are in same sign. This is only happen for proton or charged particle, electron, okay, for only charged particle, whereby the forces involved here is not a direct contact force, is field force. So let's take a look on perfectly inelastic collision. So if we refer to this diagram, okay, before the collision, the particle moves separately. Okay, let's say M1 having V1 initial moving to the right and M2 has V2 initial moving to the left. Okay, after it collide, after they collide, both of the particle move together. This is perfectly inelastic collision. They are going to move together, stick together, and move with the same velocity, right? So in this case, for the perfectly inelastic collision, momentum is conserved. Okay, so it means that momentum final is equivalent to momentum initial, right? So momentum initial, since we have two particles, right? So you have to consider both. Okay, the momentum for the object 1 plus momentum of the object 2 is equivalent to momentum final for both of the object, because since they stick together, so we just add up and move with the same v, so we just simplify the equation into this. Alright, so v final, okay, of the particles, okay, can be rearranged from this equation and in terms of this one. For elastic collision, okay, okay, besides the momentum is conserved, okay, similar to the case. So since it's elastic, they are not going to stick together, right? They are going to move with their own velocity. So momentum final for object 1 plus momentum final for object 2 is equivalent to momentum initial of object 1 plus momentum initial of object 2, right? So the information that very important is actually conservation of kinetic energy in elastic collision. For elastic collision, kinetic energy is conserved. It means that kinetic energy initial is always equivalent to the kinetic energy final. So means that, okay, kinetic energy for object 1 initial plus kinetic energy of object 2 initially must equivalent to kinetic energy final for object 1 plus kinetic energy final for object 2. Alright, we can visualize the situation of elastic collision into this. Okay, you have M1, M2, okay, having their own velocity, moving in opposite direction. After they collide, they're going to move in their own, okay, V. So for this case, momentum is conserved. Okay, the kinetic energy also conserved. Okay, but for inelastic collision, yes, momentum is always conserved, but the kinetic energy is not conserved. It means that kinetic energy final is not equivalent to kinetic energy initial. Okay, for elastic collision now, if we open up the equation, okay, this is conservation of kinetic energy, and simplify the equation into this, open up the square here, okay, and make use also the conservation of momentum. Now we are going to simplify the equation. You will get this one, and then finally you can have a simplified version, okay, which is equivalent to this. Okay, you may memorize this one, please do so. Okay, memorize this equation, the final equation, but be careful. Okay, this equation only meant for elastic collision. You may not use this equation for inelastic collision, because remember, this equation is derived by make use of conservation of kinetic energy and also conservation of momentum. Okay, so that two information are meant for elastic collision. So example 9.4, the executive stress reliever, an ingenious device that illustrates conservation of momentum and kinetic energy is shown in the photo here. Right, it consists of 5 identical hard balls supported by strings of equal length. When ball 1 is pulled out and released after the almost elastic collision, between it and ball 2, ball 1 stops and ball 5 moves out as shown in the lower figure, like this. Okay, if ball 1 and 2 are pulled out and released, they stop after the collision and ball 4 and 5 swing out and so forth. Even if 4 balls, okay, 1 until 4 are pulled out and released, 4 balls, okay, which is 2 up to 5 swing out after the collisions. Okay, is it ever possible that when ball 1 is released, it stops after the collision and ball 4 and 5 will swing out on the opposite side and travel with half the speed of ball 1 as in figure? Half. Okay, so this is what we want to investigate. So based on conservation of momentum, make use of that, substitute it here, then open up the bracket. This is for object 4, this is for object 5. Okay, ball 4, ball 5. Okay, which is going to give us 1 over 4 mv squared. What does that mean? What does that mean? To have this kind of results, it is impossible, because it is not conserved, right? For elastic collision, remember, okay, P final mass equivalent to P initial. Yes, K final mass also equivalent to K initial. Okay, this is must be conserved, but not for this case, isn't it? That is why it is impossible. Right, a similar analysis can be applied to the billiard ball collision in the opening storyline. In that case, there are two storyline in your textbook, okay, for this chapter. Okay, in that case, there are 2 billiard balls in contact rather than 4 steel balls, as in this case. When the cue ball strikes the pair of balls, the only way to conserve both momentums and kinetic energy for the system of 3 balls is for only 1 ball to leave the collisions. That is why the reasoning, okay. Therefore, the purple ball remains stationary just like balls 2 through 4 in the figure on the right. Right, consider what would happen if ball 4 and 5 are glued together. Okay, now what happens when ball 1 is pulled out and released? Okay, so let's try to solve it. Conservation of momentum. This is, okay, conservation of momentum now. Now because it is glued together, then you have 2m, okay, because they are stick together, glued together. Based on conservation of kinetic energy, what will happen? You will have, okay, V4 and 5, okay, is 2 over 3 of V1 initial. Okay, and V1 final is equivalent to negative of 1 over 3 V1 initial. So that means that the ball 4 and 5 going to move together with 2 over 3 of V initial of ball 1. Okay, and ball 1 going to move, okay, in opposite direction or bounce, okay, and having 1/3 of its initial velocity. That is the meaning of our finding. Alright, now example 9.5, carry collisions insurance. 1,800 kilogram car stop at a traffic light is struck from the rear by 900 kilogram car. Okay, the 2 cars become entangled, moving along the same path as that of the originally moving car. If the smaller car were moving at 20 meter per second before the collisions. What is the velocity of the entangled cars after the collisions? Okay, so change in momentum equivalent to 0, conservation of momentum. It means P final equivalent to P initial. So initially only car 1 having V, right? And then finally they are entangled and moving with the same V. Alright, so from here, rearrange. Okay, our V final is our interest. So you will see here, you will have 6.67 meter per second as the V final for both of the cars. Suppose we exchange the mass of the cars. Okay, let's swap the mass. What if a stationary 900 kilogram is struck by a moving 1800 kilogram car? Is the final speed the same as before? Okay, supposedly the final speed is higher. Let's prove it. So from the equation of V final, okay, let's substitute. Now our M1 is 1800 and our M2 is 900. You see here, okay, it's going to be 13.3 meter per second in comparison to 6.67 meter per second. So definitely the final speed is higher. Right. Example 9.6, the ballistic pendulum. The ballistic pendulum, an apparatus used to measure the speed of a fast-moving projectile such as a bullet. A projectile of mass M1 is fired into a large block of wood of mass M2 suspended from some light wires. The projectile embeds in the block and the entire system swings through a height h. How can we determine the speed of the projectile from a measurement of h? Okay, the height where the block and the embed bullet swing together and finally reach maximum height. When we talk about maximum height, bear in mind the V whenever the system reach maximum height must be 0. Okay, so this is a solution for the case of the ballistic pendulum. Okay, if we can visualize the situation of the ballistic pendulum just now, this is the situation A, whereby the bullet is in motion going to strike the block. Okay, in situation B, okay, collision already happened. The bullet embed itself within the block. Okay, at this level we put it as situation B, and then now the block going to swing together with the bullet and reach maximum height. Okay, and eventually stop a moment. So at this situation, I symbolize it as situation C. Okay, so let's take a look on situation B. What we can have in terms of analysis of situation B, we are going to use conservation of momentum. So based on conservation of momentum, P final equivalent to P initial. So P final we have M1 plus M2, okay, and this is from A to B, okay. From A to B, we are going to use conservation of momentum. Okay, so P final, momentum final after the collision is M1 plus M2 times V at position B or situation B as the V final for the collision case. Alright, so this is P initial, M1 V1A, okay, after bullet, okay, plus M2 supposedly V2A, but we know that the block is stationary, okay, at the moment. Alright, so this block is stationary. That is why, okay, the V2A equivalent to 0. So our interest, we don't know information of VB here. So put the VB as our interest. Okay, we have equation 1. Now, let's analyze the situation C. Okay, so from the moment it's going to move and swing up and finally stop when it reach maximum height, we may use conservation of energy for isolated system, whereby, okay, delta E internal now does not exist. So this one is 0, that is no friction, right? So what we have in our hand, delta K plus delta U equivalent to 0. Within delta K itself is K final minus K initial. delta U is U final minus U initial equivalent to 0. So, initially, the block moving together. So, it has VB. But finally, okay, it stopped a moment when it reached maximum height at position C. Right? So, that is why V at C equivalent to 0. And this is the K initial half M1 plus M2 embeds, because it's embeds moving together, times with the VB squared. Okay. And then U final is M1 plus M2 G Y at C, which is our H. Okay. And U initial is at the ground level here, or 0 level here. So Y initial is 0. Okay. Bear in mind, all of this equivalent to 0. So here we have equation 2. Okay, yeah, so you have to substitute equation 1, the VB, into this. Okay, substitute the VB, the equation 1, into equation 2. You will simplify the formula. You will figure out V1A is equivalent to this. Right? That is how to answer for the ballistic pendulum case. Example 9.7, a two-body collision with a spring, a block of M1, equivalent to 1.6 kilogram, initially moving to the right with a speed of 4 meter per second on a frictionless horizontal track, collides with a light spring attached to a second block of mass M2 equivalent to 2.10 kilogram, initially moving to the left with a speed of 2.5 meter per second as shown in the figure on the left. Okay, this is after collision. Okay, the spring constant is 600 Newton per meter. A, find the velocities of the two blocks when they are again moving separately after the collision. So sort of bounce. Okay, so first thing we're going to do is conservation of momentum. Okay, since they are bouncing, so means that they are experiencing elastic collision. The second formula or concept that we're going to use is conservation of kinetic energy. Remember, this equation is derived from conservation of kinetic energy. Make use of this T information. You are going to solve it simultaneously. So if you refer to this, okay, we are doing the substitution, okay, and then finally we figure out one of the unknown V2 final, okay, V2 final equivalent to this. If you substitute the rest of the information, you will get the V2 final is 3.12 meter per second. Bear in mind, okay, be careful, the negative sign for each of the velocity, okay, you have to consider it, okay, bring it along within your calculation. Okay, then once you've got the V2 final, okay, substitute into this equation to figure out V1 final. Okay, then you will get negative 3.38 meter per second. Negative mean in opposite direction to this one. Alright, so the most important part is you have to memorize this one and also this one, okay, for elastic collision. Right, B, determine the velocity of block 2 during the collisions. At the instant block 1 is moving to the right with a velocity of positive 3 meter per second as in the figure. Okay. So again, conservation of momentum, okay, and then the one that we already derived in previous equation, right, or slide, okay, V2 final equivalent to this. Okay, now substitute the information given to us, right, you will get V2 final negative 1.74 meter per second, means that in opposite direction to the 3 meter per second. C, determine the distance of the spring is compressed at that instant. Okay, so by using delta K plus delta U equivalent to 0, there is no delta E internal for this case, okay? There is no friction considered, right? So delta K means that K final, this is K final, right? For object 1, this is K final for object 2, since we have two objects, right? And all of these are K final minus, remember, K delta K means that final minus initial, right? This is K initial of object 1. This is K initial of object 2, right? And here is your delta U. Okay, this is your U final, U spring final minus U spring initial, right? Okay, so our interest is compression of the spring. So our X is our interest. So rearrange the equation based on as the X has the title, right? Then substitute the information given to us, all of them. Then you will get your X is 0.173. Alright, now let's continue to collisions in two dimensions. When we talk about two dimensions, it means that this is also a kind of glancing collision, we call it, whereby the V involved must be in components, okay, X and Y at least. Okay, it might be also in Z axis. Alright, let's take a look on this diagram. We have two objects here having masses of M1 with V initial. Okay, and M2 is stationary, all right, before collision. And then the M1 going to collide with M2, going to strike M2, whereby at the end of the process, the M2 is going to move downward like this with V2 final. Okay, and M1 going to move upward like this with V1 final. So if we refer to this, each of the V having angle from the horizontal. So for V1 final, it has X component and also Y component based on this data. So it goes the same for the V2 of M2. Okay, V2 final in terms of X, V2 final in terms of Y. So when we talk about collision, doesn't matter whether it's two dimension or one dimension, okay, conservation of momentum always take place. So since we have components, means that we have to consider conservation of momentum in terms of X component as well as Y component. So if we open up this conservation of momentum in terms of X, we have Px initial equivalent to Px final. Initially, only object 1 has the momentum because only object 1 has V initial. Alright. For object 2, there is no V, it's stationary initially. That is why P initial of the M2 is 0. Okay. Then, this one is the P of object 1 final. Okay, this is P initial of object 1 plus P initial of object 2 supposedly equivalent to P final of object 1 plus P final of object 2. But then since object 2 is stationary initially, P initial of object 2 is 0. Okay, and in terms of this, we are considering all of it in X component, right? So since we're talking about X components, so V final for object 1 is actually V1 final cos theta, okay, which is this one, right? Then for the V final of object 2 in terms of X is V2 final cos phi. Right. Then in terms of Y component, go the same. Okay, Y component, okay, both of the objects whether M1 or M2 does not have any V along Y initially. That is why P initial is 0. So P1 initial in term of Y plus P2 initial in term of Y. Both of them does not has any V along Y initially. Alright, and this term is actually V1 final in term of Y. Okay, so this is P1 final in term of Y plus P2 final in term of Y. Why is it negative here? There is a negative sign here, right? Because the V to Y final is pointing downward. That is why it has negative sign. Okay. So since this is a kind of elastic collision, okay, because they are moving with separate V, okay, kinetic energy also conserved. So kinetic energy initial must equivalent to kinetic energy final. So initially only object 1 has the V, therefore kinetic energy initial is in term or coming from M1 only. Okay, equivalent to this is kinetic energy final for object 1. This is kinetic energy final for object 2. So if we refer to this, okay, you have to use the solid or the resultant V final. Okay, the resultant V final for object 2. The resultant V final for object 1. Okay, because this is energy. It has no components. Right, let's take a look on example 9.8, collision at an intersection. 1,500 kilogram car traveling east with a speed of 25 meter per second collides at an intersection with 2,500 kilogram truck traveling north at a speed of 20 meter per second as shown in the figure. Right? Find the direction and magnitude of the velocity of the wreckage after the collision, assuming the vehicles stick together after the collision. So this car having initial velocity in terms of x positive, and this truck having initial velocity in terms of y and is positive. They're going to collide and then finally move together with V final having theta from x-axis. So conservation of momentum, okay, initially in terms of x, only object 1, okay, has the velocity, right, in terms of x. For object 2, its initial velocity in terms of y, remember. So for momentum initial of object 2 is 0. Okay, then this is since finally they move together, okay, in terms of x, it's going to be V final cos theta. Because, okay, from the given information to us just now, okay, from the given information just now, okay, the V of both of the car is in terms of this. This is x-axis and this is y-axis. So V final of the both vehicle, okay, has component. This is V final cos theta, x component, and here is V final sin theta, y component, right? So in terms of x component, we are going to use V final cos theta. So conservation of momentum in terms of y component, right? Initially, only object 2 has initial velocity or in terms of y, right? For object 1, it has no velocity in terms of y. That is why the momentum initial for object 1 in terms of y is 0. Okay, and in terms of final momentum, both of the cars and or vehicles moving with the spin the same speed and angle, right? So v final sin theta for the y component here, this one. Alright, so then since we have two equations, okay, this equation and this equation, we have sine theta here, we have cos theta here, theta is not given, so why not we simplify the term here, we make a ratio sine over cos, okay, because sine over cos is equivalent to tangent theta. So make a ratio of this equation. Let's say this is equation 2, this is equation 1. So what happened here is actually a ratio of equation 2 ratio to equation 1. The purpose is to simplify the term for theta. Alright, so now, okay, you have sine over cos become tangent. So you have also the ratio of M2 V2 initial over M1 V1 initial. How about M plus M1 plus M2? Cancel out each other, right? So imagine this one over this one. Okay, so cancel out. This one going to be cancelled out. This one also going to be cancelled out. That is why we left with sine theta over cos theta. So now to figure out theta only is up tangent of the whole bar of this. Okay, substitute the value, you will get 53.1 degree. Okay, so once you get your theta, you may now, okay, make use of this information to figure out V final. Okay, if we refer to this equation, seems like, okay, it's using this equation. Okay, it's using second equation. Substitute, make use of this equation. This is equation 2. This is equation 2, okay? Right? Then you're going to substitute theta with 53.1. Then you're going to figure out V final for the both of the cars, 15.6 meter per second. It also can be done if you want to use the equation 1, also can, no problem. Okay, the center of mass, okay, for each object we know that previously the mass consists within an object is actually combination of masses for the structure of it, but the common that we used to is, for example, is this shape, right? A block. We know that the center of the mass for this kind of object is at the center of it, right? How about, okay, a person also at the center of it. Okay, so here is the center of mass of this person. All right, then how about if we have undefined shape of this kind of object? Okay, where to put the center of mass? A lucky guess, probably we're going to say it somewhere here. Okay, but actually we do have a technique to know, to determine the center of mass for this kind of object. So we have to begin with, okay, actually to have this kind of object, it might consist of a few sections, isn't it? It might combine this kind of portion within the object itself. So we have to actually calculate one by one and then combine them. Okay, so goes the same to this kind of shape. Okay, where is the center of the shape? Center mass of the shape of this object. Okay, by lucky guess, we are commonly, we say that it's in the middle. Alright, so actually, we have to determine the center of the mass by proper method by using this system. Let's say we have a combination of, okay, M1 and M2 as one system combined. So the center of the mass, okay, for combination of M1 and M2 must be calculated by using, since there is no position along Y, right? So our consideration going to be in X axis only or position only. So if you see here, M1 is positioned at X1 from the origin, and M2 is positioned at X2 from the origin. Okay, if we look at on this diagram, M1 is positioned at X1 from the origin, and M2 is positioned at X2 from the origin. So, to calculate the center of the mass, it also means that the average position of the mass, okay, is equivalent to, okay, M1 times its position plus M2 times its position over the average mass between the objects. Okay, so this is, so for example, okay, let's say X1 is 0, X2 is D, M2 is 2 times M1, so means that, and the M1 is M, let's say M1, M2 is 2 times M1. Alright, from that, substitute the rest of the information, you will see the center of the mass is 2 times D, 2/3 of D. Okay, so the D here, so 2/3 of the D probably somewhere here. This is the center of mass for the system combined between M1 and M2. Okay, so this is the way to calculate center of mass for a system or an object. Right? So means that if you have more than two items or object within a system, you have to do or repeat this calculation until up to the n number of the object within a system. In simple, this equation can be transferred or expressed in terms of this. Okay, actually it's the same. So this apply for X position, goes the same to the Y position and Z position. Right. So we can have another approach by using position vector. Okay, so if we want to apply in terms of position vector, we are also going to repeat the same method of calculation. Okay. In terms of position vector, we can visualize it in terms of this. So position vector always refer from the origin to the position of that particular M or object. Here's a part we've learned about center of the mass. Okay, now with regards with the ground of the earth, okay, we want to know what is the center of the gravity. Okay, so it means that where is the center point where the gravitational force acts on the object. The center of the gravity, the weight going to be acting like this. So this point is the center of gravity for this object. And how about this one? To the respect of the ground, we always visualize the weight. Okay, the force due to gravity or weight at this position. Okay, so the center here will be center of the gravity. Goes the same to the block here. Okay, so this is the weight. So here is the center of the gravity. How about if our block right now is placed on incline? Still the same. Where is the center of the mass? And the center of the mass also going to be the center of gravity for this object. Okay, so we have a method, a classical method to determine where is the center of the gravity. Alright, if let's say you have a wrench here, is hung freely first from point A and then from point C. So from point A, okay, if we attach a point, okay, and make as a reference, that as a reference line passing through point A and point B, and now if let's say we attach the rope to point C, it's a reference line that passing through, okay, the wrench, you will see intersection point between the point, the reference line between A to B just now and C to D. Right, the intersection of the two lines that passing through our object, you may try any other part. You may have another rope tied here or another rope tied here, okay, and do the intersection line. You will see that the point where all the lines intersect is considered as the center of gravity. Okay, that's all for this topic. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture. Assalamualaikum.